I was saying that I wasn't quite sure when I was going to meet the community again. It actually took me 2-3 years to realize the potential, the great potential of intersecting AutoML methods with optimization techniques and what AutoML can do for optimization and vice versa. And actually now I'm quite convinced, so I'm happy to be here and share a little bit of my experience and of that journey that brought me here to really work in that interface. When I sent to Marius the title of my presentation, I called it Dynamic Selection and Configuration of Optimization Algorithms from Parameter Control to AutoML. And then Marius came back to me and said, can we please add hyper? So that's the first big difference between AutoML and optimization, is what you call hyperparameters for me are control parameters or just parameters. But I think we can figure these like minor things, we can figure them out as we go. Okay, since it's a summer school, I don't know, I think we have a lot of nice interesting topics and so on to discuss. I think it's also nice to meet the lecturers. So I decided to give you a little bit about my background. So as Marius mentioned, I'm in Paris since 2013, working for CNRS. And when you think of Paris, you think of an Eiffel Tower, perhaps, you think of a nice city, and that's all true. I mean, please come visit us. It's a great place, but it's not only great as a city, it's also actually a very, very great research environment, in particular if you like to do computer science and mathematics. I have a great position, Marius mentioned it, because I can spend 100% of my time just on teaching, just on research, and I can do just on research, and I can do as much student supervision, as much teaching as I like. So I do like student supervision quite a bit, so I do, but yeah, up on me to decide. But I'm not originally a computer scientist, and that's also something, I mean, it's not, as Marius mentioned, I mean, it's not only bridging optimization and AutoML, but it's also, for me, a lot bridging theoretical aspects of computer science with more applied aspects, and I'll come back to that during the talk. So I'm a mathematician by background, and that's really how I started. But I got interested in computer science when I worked as a business consultant for a McKinsey company, where I was a bit frustrated because I came there as a mathematician and I thought, oh, we have all these cool optimization techniques and hello world. But then pretty soon I had to realize that all those nice techniques are nice on paper, but not so nice in practice. So I figured out that actually in real world, and it was a big surprise for me, I have to say that, is that heuristics and black box optimization are pretty much everywhere. And so they're used to really optimize some of the most important problems that we have as a society, as a company, and so on, are based on heuristics and very often on black box optimization. I found it very frustrating at the time. And I found it even more frustrating when I then reached out to a few professors and asked them, what can you tell me about black box optimization? And the answer was pretty much nothing, or not so much, not as much as we would like to know. So I thought, wow, I mean, that's really frustrating. So this is where we have to invest. We have to develop better black box optimization techniques. And that's why I'm here, trying to help a little bit understand how we can use these techniques, how we can develop efficient algorithms, and most importantly, which kind of techniques to apply for which kind of problems. So yeah, I saw that big gap and then decided to do a PhD. I did that at the Max Planck Institute in Saarbrücken. Back then my focus was more on theoretical aspects of computer science, in particular trying really, we have seen it in the talk this morning as well, like theoretical bounds, convergence bounds, these kind of things, complexity statements. This kind of problem is hard. There will these kind of things that interest me quite a bit. But don't be afraid. I think your talk was much more technical. You had much more formulas than me, so you can relax. Don't be afraid. We had a long talk this morning, very engaging. but I want you to stay awake for the rest of the talk. So instead of minimization, I will maximize. For me, optimization. So we know what is an optimization problem. We are given a function f. This is how people in the math course would explain it to you. You have this function f, and all you have to do is to find an x star so that f of x is as large as possible. That's optimization. And for us, I mean, I don't need to spend a lot of time on this black box optimization. Well, we don't know f. And all we can do is we can propose a solution y, and then we evaluate that solution either by running simulations or perhaps by actually doing physical experiments, or by conducting some user studies to ask people how they like this new product. And then we get some feedback about the quality of y, so we receive f of y. Yeah, the first point, simulation, I think, is what you do in your everyday business, but we also work with people actually then crashing a car against a wall and stuff like that, which is obviously more expensive. Okay, and then, so we learned that y has is quality f of y, and then we can use the knowledge about these evaluations to decide which candidates to sample next. We evaluate it, we receive information about the quality, and we continue until we are happy. Yeah. But are we happy in reality? Very often not. So I guess this is in my setting. I do that until I'm happy. This is the theoretical side. Okay. For you guys, I think the word is not like this. For you, it's more like that. You do that until you run out of budget, and then you try. Yeah. You have no more budget, so all you can do is you can say, oh, the best X that I have seen is this one. Or based on the information that I've gathered so far, I suspect that that solution is the best you can have for or the best that I found. Yeah, so I changed it a little bit. The key objective for this talk will be to find a good solution using as few function evaluations as possible. And that's perhaps a little bit different from other talks you have seen this week, is that I really mostly care about like query complexity, like the number of evaluations that we do. That is something that for now, I mean, I'm often neglecting completely CPU time and so on, but of course, if you implement things, you also have to take them into account. Okay, so applications of black box optimization, I already said it, it's everywhere. And I think it really has a big impact on how efficiently we can or effectively we can use our resources. So wherever we need simulations or experiments, and I mentioned a few applications, biology, engineering, very typical applications, because we do not have an explicit formulation. We don't know the quality of an input. We really need to do these experiments. And of course, I mean, you guys have it in your machine learning, AI applications. Pretty much everything is black box as well. Okay, but there are other applications of black box optimization. For example, maybe we do know what the problem is. Like, think of TSP. I know the graph, I know where the cities are, I know the distances between the cities, yet it's a difficult problem. Yeah? And yet it is so, even though the instance is there, the function is there, I can do whatever magic I want to do with my mathematical background. But very often I find myself in a situation where I simply don't know what to do. And very often I don't have the time to go and develop an algorithm for my problem. So what I will do very often is I will just rely on heuristics. Yeah, local search, for example, random search, grid search, all these things we have heard this morning. And then there's a third type of application, and that's quite important as well, and these are privacy concerns. So again, maybe we do have a model, maybe we know exactly what the problem is, and we know what we want. We don't have the tools to do that, but I want you to solve it for me. But I don't want to share my data, and I don't want to share the model with you because it's very sensitive. So then, but in order for us to communicate, I will allow you to make queries, and then I will tell you whether the solution is good or not good, or I will give you some indication of where you should drive or find good solution. So all these, and yeah, for us, it's mostly this, this application where we really need to run simulations. Okay. So black box optimization, it's pretty simple, right? I mean, we have the algorithm, we have the black box, and we interact with the black box by asking queries and then evaluating, receiving problems. So there's essentially only two questions we need to answer. How many solution candidates should I evaluate? And how should I generate them? That's all, right? And even the first question, I mean, typically we are constrained by our computational resources or by the experiments that we can run. So very often we don't even get to decide how many candidates we can evaluate, but that's determined by our infrastructure or by our resources. So really only we need to answer the question, how do we generate the solution candidates, like these, candidates that we want to evaluate. Okay, but let's do it, right? I mean, here's that's easy. So I brought an example for you. There's even a prize and some chocolate. Because I knew I was going to be the second speaker. You're going to be tired, but to keep you awake. So I accept suggestions for where to find that. Remember, we maximize. In the middle. So 10.5. Oh, sorry. No, I should do this. 10.5, yeah, this the middle, or single. You can make a guess. The one who has the best guess wins chocolate. Sorry for people in Hanover. You can ping Marius too. Okay, so 10.5, 0. Are you happy? Great. Frank is happy. Okay. Any other bets? Yes. Sorry. 4. Okay, wait. Now I need to. Have this more. 420. 570. Wow, 570. Are you happy?
I don't know.
But you're a little bit more happy than Frank. Yes. Are you still happy, Frank?
I am very happy, Frank.
Yes, you're still happy. Okay. Okay. Yes.
15.8.
15.8. 808. That's good. Yeah.
9.9.
9.9. Minus 243.
Yeah. I'm minimized.
I don't ask you if you're happy. Yes.
7.17.
Wait, 17. 7. Okay. 768. Yes.
2.2.
2.2. Minus 12. One more guess. Yes. 10, 13, this one? 484. Yes. 9, 10. This one or this one? This one. Minus 274.
Optimization around the cut.
We are maximizing, no?
Yeah. No, but around
814. This one? 752.
There's no bias here. So if I am giving a chance, only one chance to guess, I will always explore it at this point. I will not
Or you
explore.
wait, right? You have the other X.
Or you wait, but I don't know what the budget is. So I really want a chocolate.
Thanks for the hints, yes. Do you want to make your guess? No?
16.8.
16.8. 770. Yes. 13.9. 15.9. 16.7. 806. Okay, last two. Last chance for chocolate. Sorry, 5? 5. Very brave.
2010.
2010. Okay, 618. Okay. Last. Okay. Which one?
No, I had one.
You had the 808?
808, yes.
Okay, so this is your chocolate? Okay, good. I won't show you the function. I can show you the function. If you're interested, you come talk to me. We didn't find the, huh? Shall I? Okay. Well, let me do this. So you can actually. No, I can also remove. But then I think it's just more impressive with the colors. So if Excel allows me to. This is how you see I'm not a computer scientist. I use Excel to. Okay, and this is how you. And this is also why you know you're not a why you are a computer scientist. You don't rely on these tools. So here's the function, and so 808 indeed is the optimum. Wow. Yeah. So, but you see, there were some regions here that you didn't find that are pretty good, and then we had that big green region over here. Yeah. Okay, ask for a piece of chocolate. That's good. And yes, you see there is some complicated function here. I mean, yeah, okay. Good. How did you like the exercise? You like it? But how did you feel? Like, did you want to go first? Did you want to? You already mentioned, right? You said, okay. You didn't know what the budget is, so you didn't like it. Okay, next time I will say everyone has one guess. Okay, imagine everyone has one guess, so we know the budget is 54 people in this room. Then what would you do? Would you go first? Would you? Yeah, last depends. Now you start to think about the size, right? If there are 54 cases, you don't want to be last, I guess. You want to be somewhere in the middle. If the search space is large. So you see there are many factors that impact your decision, right? We have also seen that people have different strategies, right? Because we had no clue whether we saw 808 quite early, but we were not sure whether this was the best value, yes or no, right? That was a lot of uncertainty in the room. And then we had some brave people who explored, yeah? But we have seen that most of the samples towards the end were really here focused, yeah? We were converging, we were doing exploitation. And this is something that in general we typically want to do with our algorithms, right? In the beginning, we want to explore a little bit, yeah? We want to see where are the promising regions where I should focus my search. And then at some point, because you see that the clock is ticking, you're running out of budget, yeah? You're starting to get nervous, and then you think, okay, now I should go and exploit. Yeah, so now I should do search around those regions which look pretty promising. This is what we want our algorithms to do. And well, just a little animation again. So in the beginning, we sample it a little bit everywhere. And also this is what Bayesian optimization, for example, does. Typically before, I mean, you didn't show it today, but typically when we apply it, we typically have what we call a DOE or initial design phase, where we do random sampling or quasi-random sampling to explore. And only then we would start with this surrogate-based approach that you have explained to us this morning. So we find which regions are interesting, we focus on them, we sample a bit more, we then narrow down the search, we find again this region, we sample a bit more, and then again until we are happy or until we run out of budget. Okay, so we don't want to do that by hand and all the time, right? I mean, I can't come here every time ask you which thing to remove to show you the function values. But so our goal is, as computer scientists, to do that in an automated, data-driven fashion. So we want to adjust the search in an automated way. And essentially, right, we said that all we have to do is we have to decide which points to sample next. That's really all we can do in black box optimization. And these points are typically sampled from some distribution. This is the most technical slide in this whole presentation, I think. So we have our either prior knowledge or things that we have already evaluated. And then we use that knowledge to decide the strategy. And this can be explicit or non-explicit. Typically this distribution is not explicit. It's not that we have to go and define what the probability distribution looks like and then we sample from it. But it can be complicated things like we do in Bayesian optimization. You have some strategy that somehow tells you how to sample the next point. Yeah? Okay, so we somehow need to adjust this distribution. And what we really want to do is we want this distribution not to be fixed over the whole search space, right? Because this would be boring, like random sampling or your prior sampling that you have shown as one of your baselines. But we want to use the information that we have to adjust or to the sampling strategy. Okay. So if you have seen this morning, we have talked about hyperparameter optimization, right? And maybe now we will do the 2.0, because what I want to take you is I want to take you on a journey to say we don't need to find, often we should not go and find one parameter value that is good, but the parameter value that I'm tuning may actually change over time. It may be beneficial to have a big parameter value in the beginning, and it may be better that it gets smaller at the end. You have shown this, for example, with your PyBO, right? You have this parameter beta, and you had this, you used it to adjust how much importance you give to the prior that the user specifies. And then what you were doing is in the beginning, you were giving it a lot of importance, and then you were decreasing the importance by this scaling it down until it essentially didn't impact anymore, and you would have your classical Bayesian optimization. Yeah, this is exactly. And this is what I would call a scheduled parameter selection. Yeah, because all you did is you had some starting point, and then you scheduled it down, like, and as time was passing by, you were essentially, I would call it accruing that importance. And that's a strategy that's actually pretty successful. If you go and talk to people doing industrial optimization, pretty much everyone knows simulated annealing. And this is, I guess, the best known black box optimization algorithm. I mean, it's unlikely, I think, still that you will find people in industry and first thing they will say is Bayesian optimization. I know you're working on changing that. Maybe hopefully in a few years that may change. But now if you go and talk to people and you ask them what kind of tools do you use, simulated annealing each and every time. Really, each and every time I talk to people in practice, they know about this algorithm. And why simulated annealing? So do you know simulated annealing? Who has seen it? Yes. Okay, I think that confirms kind of. And the basic idea of simulated annealing is that we are doing a local search, but as we may get stuck in local optima, like this red one, when we sample around it, the solutions may be worse. And now we will nevertheless accept such a solution, meaning we will continue our local search around this point that is not so good, like this blue one here. But we will accept to go there only with a certain probability. And that probability that I accept to go from this good solution to the bad solution, maybe I should go here with the camera, sorry. That probability depends on how much worse this blue solution is. And it also depends on how much time has passed. Yeah, so in the beginning, I may want to accept very big decreases, and then in the end, I will only accept. And this, in classical simulated annealing, the way we change this probability of accepting solutions that are not so good is exactly the same way as you have shown this morning, as in PyBO. We have a schedule that somehow decreases or cools this temperature. Yeah. Okay. There's another one of my main research topics is an evolutionary computation, where essentially you have a parameter, we call it the mutation rate, but essentially all it is just it determines the probability distribution of the radius at which I sample. So I'm doing like local search, I have my solution, I sample a random radius, and then I search around that radius, take the solution, and then I do greedy search essentially. And again, in order to converge from a global search towards a local search, I can start with a large mutation rate or large step size, if you like, and then decrease it over time. And then I converge. And in Bayesian optimization, you can also do similar things. Here I mentioned as an example, we can change that acquisition function, so we can start with something that would favor solutions where we have big or high uncertainty around the solutions. And then towards the end, what we would ideally want to do is we would want to exploit and then rather go with solutions that probably have a higher probability of improving over my current bets. Okay. So these strategies we have seen it, right? PyBO, super effective, simulated annealing, known by everyone in industry. The evolutionary computation, also very super efficient. But it requires a well-designed schedule, right? And there were questions this morning: how did you choose the beta? How did you choose the trade-off between the two? We discussed it quite a bit. In simulated annealing, this is like a black art, if you like, to find these cooling schedules. But hey, we are AutoML people. Finding a good, well-designed schedule shouldn't scare us, right? Because we can do what you did for your PyBO. We can go and do some experiments and just check what that trade-off should look like. And then we come up with something, with some heuristic that cools this parameter, and then we're happy. And then we hope, yeah, so this, no problem. We can do that. But, sorry guys, I think it's still suboptimal and it's far from where we should be happy, yeah, with. I think we can do much better because with these scheduled cooling strategies, we're completely ignoring the feedback that we obtain from our optimization process, right? All we care about is how much time do I have left, right? And I don't care whether I have done great things or seen this or that, and I'm not even trying to match that to other experiences that I may have had in the past, right? So I think it's hugely suboptimal, and I think we should try to do better. And this is why I'm here, to tell you, first of all, that this is an issue, and to show you different ways how we can actually rely on other knowledge, or try to at least react to what we see during the optimization process. Okay. So this brings us to self-adjusting parameter selection. And here, essentially, we also want to change parameters that determine our search. But we want this change or this update to depend on our optimization process. So for example, was I very successful in the past? Yes or no, and so on. I take this into account. I look at all this and then decide what to do next. And here's a very, very simple way of doing that. This is the so-called 1+1 evolutionary algorithm. It's not very important for the rest of the talk how it works, but let's imagine we are maximizing a function that is defined over binary strings of length n. And all we do is, this algorithm does it chooses an initial point uniformly at random sum, so we start somewhere. And then in every iteration, what I'm going to do is I'm going to what we call mutate that point. That just means I'm somehow creating a new point around. Okay, I'm creating that point y. And then I do greedy selection. If y is at least as good as x, I will continue my search here. Like local search, like greedy local search, the only difference essentially is that the way we come up with new solution candidates is that we do not only search in the direct neighborhood, but we have some probability of searching further away. More formally, just this will be my only slide, I think, about evolutionary computation. But essentially what we do is, or in practice what we do is we would copy, y would be a copy of x. Yeah, so it is the same point, but then we go and change, since we're here in a binary alphabet, we are going to flip each bit with some probability p, and often p is chosen as 1/n, so that on average we would change just one bit. So we do a local search, random local search, but that p may also be larger. If you use p 17/n, then on average you will make 17 flip changes, right? And then I said before that one of the things we would like to do in evolutionary computation is to essentially have a large p, meaning we do large steps in the beginning, because then we can go and do big jumps, explore. And then if we decrease p, right, then we shrink, and if p goes to 1/n, then we will have in the end local search. Okay, and this is what we can do in a scheduled way, as we have seen on the previous slide, but I think we can do better. And here's a very simple strategy that people use, and it's actually quite, I mean, I find it fascinating such a simple rule can work well. We call it the 1/5 success rule. And all we do is the following. We initialize P with some initial value, 37 over n, if you like. Yeah? And then we will let the process figure out the good value for P by itself. So what we will do is we will, again, we have our starting point, we have our initial P, we create our new, what we call the offspring, our new solution Y. We check if Y is at least as good as X. If it is, then hey, that was good. But it's also, hey, there are better solutions. So let's try to be even more aggressive. Yeah? Let's do even larger jumps to see if we go further away from where we currently are, we can find even better solutions. So what we will do is we will replace this parameter P by, I mean, we will just multiply it by some value A. Think of A as being factor 2. Yeah? So instead of then next time doing 5 steps, I will do 10 steps. So I will do even, with the hope that I do even more progress. And if I'm not better, if my new solution that I sampled 5 steps away was not so good, I'm going to reduce, because yeah, maybe I should rather focus around the point where I'm already at. So I will decrease my P from 5 to, let's say, B times like maybe 2.5. Yeah. Okay. Looks super simple, and that's all you have to do, and that is quite efficient. Yeah. And why is it 1/5 successful? Because typically we put the parameters A and B so that so if you are successful in 1 out of 5 iterations, yeah, so now this is the point where you see we're now in evolutionary computation. Typically we have large budgets here. So this is really meant for applications where each evaluation is not very costly. So typically have like thousands of evaluations. So having 1 out of 5 success is considered to be good. And then we want the process to be stable. Yeah, that is just some rule. There's some theoretical reasons why to do that. I'm not going to talk about that. But this is, even if the parameters are not necessarily 1 to 5, we still call it the 1/5 success rule as an umbrella term for this type of parameter. Yeah, what we call self-adjustment. Okay, so here's an example. So we applied it on a problem, which I'm not going to explain. And you see in black the optimal action that the algorithm could have taken. And you see in red the action that the algorithm has taken with this very simple 1/5 success rule. And I think, I don't know, when I see it, I'm pretty amazed to see such a great fit between the theoretically optimal things that you could have done and what the algorithm figures out by itself, what it has done. This is averaged over, I don't remember, maybe 11 runs, I think. So on average, it's behaving like the optimal schedule suggests. So I found that pretty amazing. And actually we could even go and prove, like mathematically prove and show that this technique indeed gives us an optimal schedule. So here, this is, I mean, forget about numbers, etc. But essentially, this is the optimal schedule that you could have. It has the performance, now I'm always normalizing by n squared, but 0.68 times n squared performance. This is the best you can do. And this 1/5 success rule, yeah, just a simple rule. If you're successful, double. If you're not successful, I halve my parameter. And it has this, provably has this optimal performance. And as a side remark, so here, this is what people would do as default. This could be the prior in the talk of this morning. Yeah, so people say 1 over n is a good value. Now, if people know a bit about hyperparameter optimization and they are smart, yeah, they know Frank, they know Marius, they know which tools to apply. They run SMAC, and SMAC may be able to find the optimal static value, which would be this 1.59 whatever. They would be better, right? I mean, sorry, so we go down, the performance improves, but we would never be able to reach this much better performance. which we can achieve if we not only try to do hyperparameter optimization, but we do hyperparameter optimization 2.0, if you like, meaning we do it dynamically during the run. We not only try to find one parameter, but we change the parameter over the run. Okay. And I want to very briefly mention this because I think it may be language that may speak to you. So we can also look at this question of which parameter should I use as a multi-arm bandit problem, which I think is something that may appeal to many of you. So we can think of the bandits as being like the different values for my parameter that I could choose. In the beginning, I don't know which parameter value is good. So my confidence in each one of them is equal, is 0.5. I have no clue. I'm going to take one of them. I will do one iteration, and I will see at the end whether the iteration was successful, yes or no. If it was successful, I will increase my confidence in this value. I will say, okay, choosing 4 was good because I found a solution that is better than my previous solution. And then what I'm going to do is I'm going to do some what you guys would probably call an epsilon greedy reinforcement learning or something like this. So with some probability epsilon, I'm going to choose a random parameter value or a random expert, if you like. And with the remaining probability, 1 minus epsilon, I'm always going to choose the value that has the highest confidence. And then I do one iteration, as I said, yeah.
Ask a very strict question.
Sure.
Because it was a little tired. So what you were showing there as a multi-arm bandit is just the discretization of the parameter.
Yes, yes. So imagine exactly. So imagine that you.
So
this is
one parameter that you discretize it into 5 different.
In this illustration, yes, 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 yes. This is one limitation, if you like, of that approach. At least if we formulate it like this, we can generalize it and have continuous. But exactly. So we do our iteration, and then we see were we successful, yes or no. If we were successful, I mean, we somehow then need to update our confidences, and we run the whole system. And you see, yeah, for example, at some point, my confidence is maybe like this. So this is probably at the end of the optimization process, where I will stay more locally. For example, if R means the radius at which I sample, yes. And now the advantage is not only that I can find the good values, but that I can actually control the values, and that these values can change, right? That in the beginning, my confidence for 4 may be good, and I see that, but with the epsilon greedy, I will have some probability, and I will realize that, okay, now this value, there's a value that gives me even better rewards during the optimization. So let's shift our confidences, and they can change over time so that I can benefit from parameters that change. Okay. There's a whole lot of things to be said about this. There are also some theoretical guarantees. Again, I mean, we can go and analyze pen and paper, computer science, and prove that such mechanisms can actually find optimal schedules. So here's an application, as we call it the 1max problem. Not important for this talk, but essentially the optimal value follows kind of this curve. And we can show that if we choose, and this is a big if we choose the hyperparameters is epsilon, for example, correctly, and the way we update the strategies, then we can have provably optimal performance. Yeah. And there's another, so first big is, but is that very sensitive with respect to the hyperparameters. And that is something that I guess AutoML people may be able to help. I think there is a lot to be done around this approach. Many people have tried. So there's a team, Harry is here as well. He comes from the team of Marc Schönauer in Paris. They have done a lot what they call adaptive operator selection. They use such kind of approaches in order to control which components of algorithms to use or which parameters to use. There's another big but. I think for you guys it's probably not so important, but this is something I'd like to discuss. For us in optimization, this is a very big problem. And this is that such kind of approaches can work only if the progress that I'm seeing at every step is a good indicator for my final performance. Yeah, and this may not necessarily always be the case. Like if you think of Bayesian optimization, what you really want to do is you want to have in the end, only before the final evaluation, you know typically what your budget is. Imagine Bayesian optimization, you apply it when you have small budget. Imagine you know your budget is 500. What you would want to do is you would want to use 499 evaluations to find out as much as possible about your problem, so that the final one that you're going to evaluate, if you even need to evaluate it, is the one where you have a strong idea about that one being good, right? You don't care if in 499 evaluations, forget about all quality of all these points. We don't care. What we want is that they are informative to us, that they give us information about the true problem, much more than those points, whether they had 17 or 18, I don't care. Yeah? I want them to tell me something. Okay. So that's a big discussion. So as I say, for us in optimization, often we may run into situations where we may also get trapped. So we see, oh, that looks good, I'm going in this direction, as you did, right? You guys did the same, right? You saw that 808. I mean, okay, it turned out to be the optimum, but very soon, many people started to sample around that point, right? But if there is a discontinuity, for example, there may be, we're focusing too much on that region too early on. So we have to be careful. Mm-hmm.
One short comment, would you please stay there that the people in Hannover can see you too?
Okay, sorry.
You're making great gestures to explain stuff.
Yes, I have to get used to. Sorry for Hannover. Sure.
Okay, so this is a big problem in this sector, right? With the evolutionary algorithms, where all of the we follow some point, which is like a local optima, but not the global one.
Yes.
Can you address this issue somehow? Are there some methods to,
okay.
escape the deception?
Okay, so the question is, now I remember, I should also recall the question. So the question is whether there are methods to avoid getting stuck in local optima, in particular in evolutionary computation. Yes, of course. I mean, there are different strategies. One would be, if you see, for example, you observe, typically what we do is we observe these parameters when we control them in an online fashion like this. And when we see that they stagnate, for example, or they go below some threshold, then we restart, for example. That's a very common strategy. So we track what's happening, and when we see, okay, this is converging too fast, or now it has converged, we would restart. Or we would not restart the whole algorithm, but we would restart the parameters. We would say, okay, now the radius, for example, at which I sampled, or this mutation rate, was decreasing too much. I now set my confidences in this framework here. I set them again, I restart them. So I don't restart the algorithm, but I restart essentially the way my algorithmic framework works. Yeah. And then there are other strategies, like I think SMAC does that as well, that you are doing the Bayesian optimization, but every now and then you add a few random points. So to make sure that you are not too much biased towards your search that may already be convergent. Yes. That's I would say one of the most common strategies. Yeah. Okay. So far, we only discussed how to control a parameter during the run, right? That's nice. I mean, and we have seen there are some theoretical examples where we can prove this is good. But and this is now the point where I think optimization, this is what I was doing before. Yeah. Then I came to Darkstuhl in 2016. I met AutoML people, and then I realized only a few years later, as I told you, but essentially it's very wasteful. We are only focusing on this particular run that we are currently observing. So we have this problem and I'm trying to optimize it. But come on, guys, we are doing so much benchmarking. We have so much data. We often, also in industry, when I'm optimizing my problem, I will have seen similar instances, for example, before, maybe the day before or the week before. So there's so much data out there that we could could and essentially should use to guide us and to help us in tuning the behavior of our algorithm in a much more informed way. Yeah. So if you did your scheduled PyBO, that's cool already because you're changing the parameter. I hope I could show to you that maybe control would be even better if there was some sort of feedback. And then somehow it would be even nicer if we could somehow rely on or make use of all the use cases that you have already evaluated PyBO on, for example, to see that if you, while you're optimizing, you realize that, oh, that instance looks like an instance I have seen 20 months ago. And what I did back then was good or not good. And then you try to use that knowledge to guide your search for your current problem. And in particular for situations where the evaluation is very expensive, like Bayesian optimization, I think is a prime example, because typically we assume every evaluation is expensive. So if in the meantime we call some machine learning model, or we need to extract features or compute features or whatever, we don't care. Yeah, it adds a small overhead that we do between two queries, but from the global perspective, the cost is negligible. Okay, so there's a lot of data out there. You guys have your own benchmarks. We have our benchmarks. So we have our optimization BBOB test suite is one that is very popular. We have the Navigrad platform, now becoming more popular because it's not only artificial functions, but also real world optimization problems, hyperparameter optimization problem, and so on. So they really try to grab a little bit problems from everywhere and also try to merge the knowledge that is available in different communities. And then one example just for you guys that may speak a bit more, like OpenML, I think is also trying to do something like this, right? So the spirit is the same. So let's collect the data, share the data, but then let's also try to make use of all the data that we have available. Okay, so we have a lot of data, and I hope we agree. I think otherwise you wouldn't be here and learn about AutoML. We should use this data to make our decisions. And we should use this data, in particular in my setting, to choose the parameters of my algorithm. Okay. Yes?
I just asked, maybe I missed this, but I mean, in your typical settings that you have in mind, how many of these parameters would you like to update on the fly, and how long would be a typical trace, or how often would you do these updates?
Yeah, okay, so the question is how often we want to do the update and how many parameters there are. It can vary quite a lot. So that is the...
just to get some feeling.
Yes, but I think this is exactly the point where I think it's good to have optimization people and ML people on board. I will come to the point later, because the optimization people typically have a good feeling for which parameters are the most critical ones. So we will break it down to small number of parameters. And for how long the traces, I mean, we often actually update after every step, because it doesn't cost us too much. As long as the updates are not too big, you can also afford that. So this, I would say, is the most typical example, is that the updates are small. And the number of parameters that we try to control, fairly small. So often we have examples where there's only 1, 2, 3, some parameters. We do have applications where we try to control 15 parameters. So, and most of them are even just binary, I mean, categorical, like binary or ternary, and only 3 of them are continuous. And actually all of the tools we have tried so far completely fail. So we do not know really how to approach this. I can tell you a little bit more about that later, perhaps, because we have tried many approaches. I think this, okay, essentially I came here to sell you a vision, yeah. I mean, essentially I came here to explain to you what we are doing in terms of hyperparameter optimization is nice, but we shouldn't be satisfied. We shouldn't stop here. We should go further, yeah. So changing configurations during the run helps a lot. We see that, we have lots of evidence for that. But we don't really know how to do that. Yeah. So my dream, and hopefully later also your dream, that you may want to work towards, is that we would like to develop an automated configuration system that uses information from external experiments, previous experiments, and our current optimization process, so that we select hyperparameters for our next iteration. And I can even, this is a dream, yeah. We do have some examples where it works. I will come to that. But we can even dream a bit bolder, yeah. Because you asked which kind of parameters and how many, and I was hesitating a little bit to answer, because I think it's not only about parameters. You can even go a bit further, and if you're doing optimization, for example, if we know we have a small budget, we are going to talk to our Bayesian optimization specialist and try to use Bayesian optimization. If we know that in my application I can afford a lot of evaluations, I'm rather going to use an evolutionary approach. And if you look at the convergence plots, or like quality over time, you will see that the Bayesian optimization is good in the beginning, but then somehow it stops being efficient after some time. Whereas evolutionary methods like covariance matrix adaptation, CMAES, maybe you have heard about it, is slow in the beginning because it needs to adjust its parameters in this same fashion as I've explained to you. But once the parameters are set, well, I mean, they're on the right track, then is being very, very efficient. So the ideal dream, yeah, and we are working towards that, is we should perhaps use Bayesian optimization in the beginning and then switch to CMAES at some point, so that you have a good, like, anytime performance, and you can benefit somehow from both strengths. Okay. Yeah, so that's really the point. I set parameters, but wherever I set parameters, controlling parameters in this presentation, you can replace it and also think about switching between different algorithms. Yeah, here's an example. I don't know what I'm doing. There's no watch in this. Okay, I have half an hour, right? Yeah. Okay, good. So this is another big difference between you guys and us guys, I think, is that we often plot on the x-axis the quality and not time, and we plot time on the y-axis. So now I'm not supposed to move, but essentially what we do is we plot how much time did it take me if I want to find a solution of quality 1. How much time does it take me? Yeah. So we see the less time it takes me, the better. So we see here, for example, what is this example? This CMAES here is quite good in the beginning, but then it loses over this BFGS algorithm. This BFGS algorithm is quite slow. So for the first targets, getting to a solution with 1 takes 100 steps, whereas CMAES takes, what is it, 20 steps? So quite a big difference. But once BFGS is in that right region, it finds I mean, it gets 10 to the minus 8 close to the optimum. So once it's in the right region, yeah, rocket speed to the solution. And now what we did, and we actually run this algorithm, if you run this blue one, so we start with CMAES, we use CMAES to find this right region with the solution quality 1. Once we are there, we switch to BFGS. The difficulty now is to inject into BFGS, whatever that algorithm is, don't worry about that, to inject the knowledge so that BFGS does not start blindly, but that you can use the knowledge from CMAES. So we call this warm starting, and then again, it just brings us to the optimum in no time. Mm-hmm.
Require knowing what a good value for a problem is. You don't know a lot about a problem, you don't know when BFGS will work.
Yes, exactly. And this is exactly, I mean, so the question is, how do we know when to switch from one algorithm to another one? This is exactly a big question for us. This is where we need benchmarking. And this is also where we need to, ways to describe. And I think this is even harder than, I mean, data is there and generating data is cheap. What is not so easy is trying to understand the state of the optimization process. So in your language, state features that describe well the current situation are very hard to define. I think that is a big bottleneck. So what we do is we run our benchmarks. We get a feeling for what is happening. We actually look inside the algorithms. We check what is happening, and then if there's certain conditions that are satisfied, we say, okay, now let's change to another algorithm. But again, this is a point, I think, where it's a beautiful topic for optimization and ML people to work together, because you need that knowledge from the optimization part to be able to warm start the algorithms and to understand which kind of features to use to describe your current state. And you need ML people like you, and we didn't, to help us define the training, how we can train such systems, how we can test whether they generalize well, and so on. All these things, I think, are tools that you guys are learning very early on, and then in this beautiful fall school, and when we bring these two together, I think we can really come a bit closer towards this dream that I'm drawing here. Yeah.
We have made some progress to it, right? I mean, we're talking now about the state optimization algorithm. I would say this should be hard probably to describe the features, but we have made some progress to describe the structure of discrete and continuous optimization. Right? I mean, it's not perfect, but there are quite a lot of what we would call meta features. Yeah, there's sometimes called landscape analysis.
Yeah, I will show an example. Thanks. Yeah, great.
So
yes. So if you're disappointed because you came here and all I'm showing to you is this dream, then hang on for a second. I have half an hour more. I'll try to be quick and get you there, but I will show you some examples where we can actually see that this is not just a dream, but it's something that is now in reach. And I remember meeting Frank in Paris in 2018, and we were discussing these things, and he was saying, yeah, it's just we don't know how to do it. And I think in these years, I mean, I'm actually quite happy to see 4 years later how much progress we have made towards actually that dream. I also wanted to say that this dream is not something that only in optimization community exists. Also in the, let's say, AutoML or ML, AI, whatever community, you guys have a similar dream. And here is this nice paper by Andre and co-authors who formally define what you call the dynamic algorithm configuration problem, which is essentially formalizes this problem in your language, telling me I want to find a policy that tells me for every given instance of my problem and every possible state that I may be in, which parameters I should use or which action I should play next, if you like. No? And we want, or you, again, this is the ML view, want to do it in a way such that the expected cost, if I average over all the instances, is minimized. Yeah, so this is formally the definition, and in this paper also some examples where it's shown how this problem can be addressed with reinforcement learning. And there's also a more recent survey paper by Stephen and co-authors available on the archive that essentially builds and extends this previous framework, also shows how dynamic algorithm configuration generalizes many of the concepts like per instance algorithm configuration and so on. I don't know how much you have talked about it already in this fall school. It's really a very, very general concept, but it really captures well this dream that we have about efficient optimization. Okay, so this was the dream. Now, welcome to reality. Sorry, I already gave it away. So I said we really need ML and optimization expertise. I think you guys are much better than us and then can help us to understand which models we should use, to how to train the models, how to generalize, and so on. And what we can bring from the optimization community is to tell you which algorithms actually to start with, to show the potential, which algorithms make sense to combine, how can we warm start, and so on. Which components to tune. This brings us again to the question, how do I know which parameters I'm actually controlling? Okay. There are a lot of key challenges. Now this is going to be a boring list, but just to show to you that it's not so easy to realize this dynamic algorithm configuration. So first is like selecting the components that I'm allowed to switch between. So which algorithms, and then for each algorithm, which are the components or the parameters that I'm going to select, how to warm start the algorithms, how to describe the state of the algorithm that the algorithm is in. The same for the instances, how to characterize the instances and how to measure whether two instances are similar. So can I even dare to transfer knowledge that I collected on that instance with this algorithm to a slightly different algorithm on a slightly different instance? How to generate training instances. Number 7, I think, is underestimated. In my opinion, is a very, very big problem, is how to assign rewards or loss or total cost, however you want to call it, to individual actions that we play during the optimization. Because in the end, as I said, I don't care if all the individual points that you evaluated were crap. I don't care. What I care about is that the final solution that you give to me is a good one. Yeah? And I will know only at the very end. And then in the very end, you will not know whether that first decision that you have taken to go right was actually the important one, or whether it was a decision in step number 37 that was the crucial one. We simply don't know. So how to distribute the reward that we get over all the different actions, no clue. Yeah? Okay, and there are many, many more challenges. I think it's a very beautiful topic. It's really, 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 I think, at the forefront of what we can do in AutoML and in optimization. So I think a lot has happened in the last 4 years, but a lot more should happen in the next. So hopefully in 4 years, I will come and show you what has happened. Okay, so Bernd already mentioned that, but we did make some progress, yes. So let me show you a little bit, some case study or one approach. Yeah. Again, this will be very optimization flavor, but this is how we approach the problem. We define first training, so we want to train our whole system, and in order to do that, we have like what we would call a default algorithm. This is an algorithm for which we believe that if we do not know anything about the problem, this would be the one that the people would use. Like in evolutionary computation, for example, this would be CMAES. Yeah, and if it's a continuous problem and you have large budget, you may run CMAES on your problem instance, and we run it for some budget, B1 steps. We run it, then we stop it. And then what we are going to do is we are going to look at the solutions that we have evaluated and the quality, and we are going to extract some features about the instance. And we call them landscape features, but I mean, we extract landscape features. So this is information about the instance, like how many local optima are there, how rugged is the function, how widespread are the Y values, how whatever, yeah, all many, many different properties. There are like hundreds of these kind of features that we can measure. And also there are features about the algorithm itself that describe, like in our case, what does the covariance matrix look like, how big is the step size, and so on. So different properties of the algorithm itself, so that we have instance features and algorithm features, and we capture them. It's like taking a snapshot. And then what we are going to do is we are going, because we have remaining budget, our total budget is B, we have only used B1 steps. We are going to run different algorithms, continuing, but warm started, continuing the search of our default algorithm that we started with. Yeah? So maybe the algo 1 is a default algorithm, and then, but maybe we decide to switch to a, let's say, differential evolution algorithm, PSO algorithm, whatever you may like, or maybe even another CMAES, but slightly different, with a different configuration, for example. Okay, and then we run it for the remaining budget, and then we observe the final performance. And then we use that data to train a model. And then when we apply this model, what we are going to do is we are going to run again our default algorithm, the same like CMAES, or in our case it was CMAES, but it could be Bayesian optimization, something like this. And actually in Bayesian optimization, this whole framework makes a lot of sense, because you anyway have this B1 thing here, as I said before, because we have the initial design, or DOE, like this random sampling that we do before we actually start a surrogate. based approach. Okay, so we run our algorithm on the problem instance, and then we, for B1 steps again, same B1 as here. And then we again extract the features. And then we feed that information into our model, random forest, whatever. Yeah, now again, you guys are expert much more than I am. And then this model will tell me which algorithm I should continue with and which parameter I should continue with. Yeah. So this is, I think, pretty close to the dream, but yeah, so we have a few cases where we get this to work and where this runs successfully, but there's a lot to be done around this topic, and ML perspective is more than appreciated to help us do that even better. In particular for us, for example, for the model, if you ask what do you use, I mean, we just use plain random forest model, as simple plain as you can think of, and it already improves and it already works. So I could only imagine that if you guys come help us do it, set up this whole pipeline, and in particular this model in a more sophisticated way and train a bit more efficiently and so on, we could do magic. Yeah.
The full algorithm here is not learned as well.
This is prior knowledge that we have. In our case, it's either prior like an algorithm which we believe to be good. So even if we decide not, it's like the best static best solver, or how would you call it? Like this is the default algorithm for which I believe that if I don't change, it's going to be the single best solver. Yeah. Yes. What was I going to say? Yeah. So it makes sense to use as the default algorithm that algorithm which I believe to be best for that type of problem. And essentially you can look at this as saying that after B1 step, I'm going to revise my decision. Am I really on the right track? Is this really the best algorithm, or should I switch to another one? It could also be an algorithm which I know is good to get me into the right region, as we have seen before with this, like I used the first algorithm, could be random sampling or whatever, get me in the right region, and then with the warm started algorithm, I only need to then do the local convergence to the global optimum. So it very much depends on the application, I would say. It depends on your budget again and your whole setup. If your budget is small, where probably default algorithm would be more a combination of random sampling Bayesian optimization kind of thing. If you know the full budget is long, we may want to do something that does a lot of exploration rather. So because the more we explore, the better the features to describe the instance will be. Yeah. There's a lot of things to be done. For example, the relevance of state features to describe the instance versus the algorithm features. I think that depends a lot also on the specifics of the budget. We did it like this. You can also think to run, if you have, for example, parallel computing power, you could run several default algorithms and combine them, right? There's a lot of things you can tune in this approach. Yeah. This is just used to generate a model. Yes, so here I have it explicitly to call my model and then to tell me what to do, which action to play, if you like. And here I only need it so that in the end I can match the final performance with these extracted features to my instance. Yeah. Or I essentially have only these features and then the final performance, and this is where I learn on. So so this is a system that we're starting to build up. As I say, it's working. I mean, results are nice, so I think it's encouraging. But there's so much to be done that I hope I can convince you guys that this is a fun and important topic. So maybe we can extend this and further. Okay. And now one topic I didn't talk about, but this is obviously something we would like to do, is when we run the algorithm, but then we have the final performance, what we would want to do is something like lifelong learning, or you guys have nice buzzwords to describe these things, but essentially we would want to feed back or to use that new knowledge that we have to adjust the model, so that the model, in the next time I call it, it has even better information, and this new knowledge is included already. Typically, this for us is not a big problem because training the models is typically cheap. What is expensive is the whole training. Okay. Yeah, so just in red, many different decisions that we need to take and that are more or less arbitrary. Okay, there's another case study that I want to mention because it has a completely different approach. And this is recent work between here the group in Freiburg, Andre and Frank, and Nguyen Dang at St. Andrews, and our team at Sorbonne, where we also want to use dynamic algorithm configuration. Now, Bernd, there's only one parameter that we want to tune, and we will use reinforcement learning to do that. So essentially what we do in this study is we are proposing a benchmark generator. So you have a different problem size, and we can tune that, and you have a different portfolio of possible actions that you can play. Now again, we have a discrete set of actions, so meaning you can either choose to, if you like, flip 1 bit, flip 2 bits, flip 4, or flip 8 bits in this example. And at every step, all I will do is I will just ask you, how many should I flip, and I'm going to flip that. And then I will tell you whether this was good, yes or no. Okay, and then at the end, what we will do is we will want to come to an optimal solution as fast as possible. And your goal will be to find for every state the best possible action that you can do so that total optimization time is minimized. And we did that by training some reinforcement learning agents using this DDQN. I'm not going to say too much about this whole approach, but just show you some nice plots. Here you see forget about this orange curve, we don't need that, but this green curve is the real optimal policy that the algorithm could play, this green, and the blue is what this DDQN approach has learned. So indeed, it was able to learn by running many times the algorithm and changing the parameters and playing with the parameters, and then using this neural network here, this DDQN approach, to then figure out if I'm in this state, I should play this action or that action. And that the match here is pretty good actually. If you look at this, if you think, oh, but there's this big gap here, then maybe this convinces you more. If we plot the final performances, we actually see that. I mean, this is what random policies would do, not too interesting, but the optimal policy and the ones that DDQN finds are actually pretty good. They match, right? So DDQN, in this case, reinforcement learning is actually very good in finding these optimal policies. But unfortunately, the whole system breaks down as soon as we increase the dimension. And this comes now to the question again, Bernd asked, how many parameters can we control? So we see a very steep decay here in the performance of the whole approach as soon as the number of parameters or the number of actions in this case that you can play, or the total size of the problem becomes too large. Okay. So I've shown to you this vision, and in order to realize the vision, I already said that I think we need to combine optimization and ML. I also think it's a lot of fun, and I think this was one of the main reasons or the fun we had with this previous study, is that we knew exactly, I could draw this green line, right? I could show you this is the optimal, look, this is the optimal policy, this is what DDQN does, and there's a good match. That's cool, right? Because we have this like ground truth that we can compare with. I think it's also an example that shows that there's actually a lot to be gained if we work between theoreticians and people doing benchmarking, more, let's say, experimentalists, or I don't know how you call yourself, if you're not too much interested in theory. So empirical computer science, and also I think it's a good way, such kind of collaborations, to then also bridge all the way from theory to final practice. Because when I show that something has n square running time, whatever, blah, blah, and I give you the whatever 15-page proof for it, it's not going to impress you. You're not going to know what the hell this can help you. And then if I benchmark, if I implement my algorithm, I benchmark it and I show to you the plots, it will speak much more to you, right? And the same is true with with people in practice that we work with. We use benchmarking essentially as an intermediate between the theoretical knowledge that we have, or academic knowledge that we have, and the practical applications to show certain effects. Yeah. So we have very different types of results and different approaches also to look at it, or to solve different ways to solve problems. So we complement each other. But in my opinion, the even more important fact about working together is that we have very different ways of looking at the same thing. So this 6 here, which is a 9 for the ML people, it just shows that we are looking at the same subject, but we look at it from different angles. And very often in meetings like this, what is the most beneficial thing is the questions that I receive and the discussions that we have, because it shows that we just have sometimes very different way of looking at it. And so I think that can be enriching and very important to develop dreams like this, and to get a bit closer to realize those dreams. So in my team, just one slide just to show that we are really bridging the whole, like we have people in our team working on very theoretical aspects of this whole topic. And we have people all the way, like Mara Ocean, for example, working at the Pasteur Institute, really with cancer data, trying to detect factors that determine resistancy in tumor treatment. Elena and Maria Laura working on structural mechanics. So very, very different type of applications. But in all these very, very different applications, the same tools essentially are used and can be useful. Yeah. So, okay, I think I will skip this. Essentially, this is our objective that we have set to us as a team. We want to have efficient black box optimization algorithms. We not only want to have a performance perspective. We don't want algorithms to be good, but we really want to understand why they are good, so that we can, for the next problem that comes, have performant algorithms much faster, because we understand what's going on. And then, of course, we want to make this knowledge available, so that it's not only sitting with us in my head, but again, benchmarking, I think, is one way, or benchmarking platforms of sharing knowledge. And so I'm mostly involved in those two projects, IOH Profiler and Navigrad, where we really make algorithms, problems, etc., data available for the community to build up on all these different things that I've mentioned. Okay, then with this, maybe I shared my dream and why I'm here, and I would say up to you to help us get it done. Thank you. Yeah, from.
It's a beautiful dream. I share it. So,
Okay.
and I do think that there's, as you say here, a lot remains to be done. One additional thing that I would really like to see, if you go back to your slide 30, okay, is to basically come up with everything that's on that slide automatically. Mm. So it's an even more ambitious dream, where you actually want to come up in a reinforcement learning setting with basically what actions should I play that are information gathering that will then tell me about what to do afterwards. So basically during meta training, you would learn, well, should I execute algorithm A for P1 steps, or should I have another algorithm, or should I run one algorithm a little bit and then another algorithm? It also really relates to multi-fidelity optimization. They're very similar, like these landmarking features that you get in multi-fidelity. You could also call them meta features of the problem. It's sort of the same thing, and that will then inform future steps afterwards. So I think it's an amazing playing field. It's really hard because this is not supervised learning. It's reinforcement learning, and reinforcement learning is, well, now mature enough to actually make progress. 4 years ago, I was like, I don't do that. Now we are doing it because DeepRL is much stronger. But yeah, I encourage people to work on this. I think this is, someone mentioned, yeah, maybe in 5 years from now, AutoML is sort of solved. But this is not going to be solved, I'm pretty sure. So.
Yes. Yeah. thanks for the comment. Yeah, I think if you know how to do HPO, hyperparameter optimization, so here's your new playground. And as you say, so much to be done. And I mean, I totally agree. I mean, also what I should say here we only decide to switch once, right? I mean, we do this V1 step and then we decide which algorithm to switch to. This is a very simple setup. And now, I mean, definitely in the full rollout, you would want to do this perhaps after every iteration, or if you're a bit more conservative, like Bernd, after every so and so many iterations. And you would want to learn when to make decisions. Yes.
Maybe to add one more thing to that, a note of optimism. I do think that this is possible. There are systems like AlphaGo and so on that is just a giant neural network, and it does something that we don't understand, that Go experts don't understand, that nobody really understands. And we could likewise build a system that tells us, well, do this, do this, do this, and that actually works great because it's optimized end to end. And then actually the question would be there, how do you go and understand systems like that when we actually really meta learn these algorithms, and we're not in these theory benchmarks, but we're in the real world? Do you have any thoughts on that?
I would say it's data-driven learning, really. So trying to understand what the system does and trying to, for us, I mean, for me, how it really works is typically I observe I see some patterns in the data. I really like, I'm the kind of person, I mean, I have no computer science experience at all. I don't program, I don't know how to write Hello World. So luckily I have students who can provide me with data. They give me these big CSV files. I open my Excel, sorry for that, but and then I go and do a lot of data crunching, and I try to find patterns. And when I find patterns, I form a hypothesis, and I say, look, I believe that this or that. And then we go, perhaps if student is still around, test whether these patterns also hold in other situations. And if so, then typically then I'm motivated enough to go and try to prove pen and paper a theoretical result about it. And we had a few, I think, quite beautiful, like this example that I've shown to you of this epsilon greedy reinforcement learning parameter control. That's just something, I mean, the student happened to have a bit more time. She did very nice work. She had a bit more time. We say, okay, why don't you just go implement it and try? And it worked, and we were a little bit amazed and a bit shocked that then we would have to prove it. But then eventually we could show it and prove, which then gives us a guarantee. And now we understand why it's working. And we also understand the limitations. And I think that's important as well to see, for example, this high dependency on the hyperparameters. Of course, something you can observe, but if you then also have a proven guarantee for this, quite interesting. So yeah, pattern matching, data crunching. How to automate that? I will leave it to you. Yes, question from Hanover, yes. What do I need to do? Can they ask questions? And I
just be here. I just in front of you. Can I ask? Can you hear us? Hello?
Yes, but wait, hang on. Yeah, wait a second, because it's too loud.
No.
Okay, can you speak? Okay, can you? Yes, now should be fine.
Test. Can you hear us? Can you hear us?
Sort of. Yes, now it's perfect.
Okay. You said, or you used some kind of paper on the following slides of this. I don't know which slide it was exactly, but you said, oh yes, that's it. You said that you used EDQN. Why did you do that?
Yeah.
I mean, it wouldn't be my first choice from the experiments that I have, which might not be as much as the researcher has, but that was quite surprising for me.
Okay, so what would be your first choice?
Well, I mean, there are, for example, Rainbow. I mean, we have soft actor critic, or Impala, if you want to parallelize things. But what exactly was the reason why you have chosen that would interest me?
The DDQN. Okay, so to be honest, so we had before this study, we had another study where Andre and also Nguyen were involved, where we tried, I think PBO is the framework, and we saw that again, this whole reinforcement learning approach is very sensitive with respect to its own hyperparameters. So what we had to do for this study is to understand very well how DDQN would respond to its own hyperparameters so that we could tune it so that it could actually learn and have performance as we can see here. So it's not that it was like default DDQN applied and oops, it works, but it really required to fine tune DDQN. And I think then it was a decision because Andre, I think, knows quite well DDQN and knows these hyperparameters. Because that's one more thing I should say is that DDQN and these reinforcement learning and perhaps the tools that you have used, I'm sorry, I'm not very familiar with those, but they are often tested in environments that are not necessarily resemble the situation that we face in optimization. And that was the case here as well with DDQN, where the default hyperparameters are tuned for applications in, I don't know, maybe some games or games typically. They were not good hyperparameters for our application in optimization. So then having someone on board, Andre, Frank, others, who know how we could nevertheless make this, because when we did the first runs, I mean, I was like, oh my God, forget about it. I mean, I was about to leave the room because the results were not very encouraging. I had my green curve, my optimal curve, and the blue curve was somewhere, but not anywhere close to the optimum. And first results were, yeah, not as we were hoping, but then with all this knowledge and refinement, then now we have a system where we understand that is suitable for such kind of applications. So why DDQN? I would say, as always, right? You start with the things that you know well, that you understand, and that you know how to adjust to your new application. But happy to, if there are people interested in trying other techniques, I mean, we have many. I mean, this is a whole benchmark generator. Also, there is Duck Bench, which I know you in Hanover know, where, again, it's a playground where we can test different ideas. And this is the whole point of this paper, is that we want to have benchmarks where we have a ground truth so we can compare the different approaches and see what their advantages and disadvantages are. So if you want to contribute to that, you're more than welcome to join the effort.
Okay, yes, thank you.
Good, then thank you very much again.